Hello, everyone. Good morning. And we'll start shortly and continue right where we were. I'll remind you a little bit of what we were doing. Very, very exciting, actually. We're um, looking to construct a function. We did already. A function with the property that it is continuous, but is not differentiable. So the derivative does not exist at any of the points. Very surprising indeed. At least, I mean, it's easy to make a function not differentiable at one point, but here the difficulty stems from doing it in every point, okay? So let me remind you where we were. Let's go to the presentation that we were looking at. So really quickly, let's review what we were doing. Our building block was this function h, and this function h looks like this. It has this graph up and down, up and down, up and down. Goes 1 unit with slope 1, the 1 unit down with slope -1, and continues on like that. For quick reference, you can think of it like it's written here. For any number, you can remove its integer part, and so write the integer part plus the fractional part. And if the integer part is even, then the answer to the function is simply the fractional part. If it's odd, then it's 1 minus the fractional part. And then after this, we looked at these hn functions, which is just take that same one, make it oscillate 2 to the n times as fast as the original one, but then divide everything by a factor of 2 to the n. So that makes it so that the slopes here are also 1 and -1, but you go up and down a larger number of times. Okay, and let me quickly show you from my Mathematica file. Okay, yeah, so that's the first one. And then here's the first and the second one, h1 and h2. There's h1, h2, and h3. h3 is this little one over here. And I have them all together so that you can appreciate how the slopes are always 1 and -1, right? And so on. Good. Then we finally showed what our function was going to be. So our function is the sum of all of these hns, or if you want to, you can think about it this way: the sum of h2 to the power n times x, everything divided by 2 to the n, and we add that up from 0 to infinity. And we showed how the graph looks a little bit like this graph over here. In this graph, you clearly see some points that are sharp turns, but at others, it kind of looks round. So you need to really zoom to realize that in reality, every single point is essentially a sharp turn. And that's what this result is about, really, right? So there is no derivative, really, at any of these points. So today, we'll talk about the derivative, actually, because if you realize that's exactly where we left off. So let me remind you quickly what we did last class. So we started by showing it's well-defined. So we proved that this series converges, right? And the fact that it converges makes it so that our function g is well-defined. And that was kind of easy to do because this h function is less than 1. So this g function, this series, is bounded by 1 over 2 to the n, which is a geometric series, and it converges. So by the comparison test, this one converges as well. That's, in a nutshell, how we did it. Next, we talked about continuity. And for the proof of that, we use this lemma. And that lemma, we'll use it again today. So let me remind you, it's kind of neat. What this lemma says is that if you have numbers with the same integer part, if x and y have the same integer part, then the difference in value of the h function is either x minus y or y minus x, okay, one or the other. And that's very, very convenient as you will see later on. So a lot of the calculations we're going to do are based on this, that the difference is either x minus y or y minus x. In particular, the absolute value is always x minus y in absolute value. All right? And for the continuity part, we also use this other one over here. So what if they don't have the same integer part, but almost? So the integer part of y is is 1 unit more than the integer part of x. What to do in that case? And we did the calculations, and in that case, we got something that is even smaller than the absolute value of x minus y. So we already used this lemma to prove the continuity last time. And today we'll use it again, the top part actually. I don't think we're going to use the bottom part anymore, but the top part we will. So remember it. If two numbers have the same integer part, when you do the difference, it's either x minus y or y minus x. We'll come back to it when we'll need it. I'll remind you where we're going to use it. Good. So using that, we could then prove the continuity. We did it on the paper. And now we'll start talking about the derivatives. So I'm gonna follow the way it's done in the book. So it starts with a little bit of a warm-up. So instead of trying to prove, just go and check every single point right away, let's start by checking one of them. So specifically 0, right? So this is the first exercise that we have on the book relating to the derivative. And it says, show that g of 1 over 2 to the n minus g of 0 over 1 over 2 to the n minus 0 is this number, n plus 1. And then prove, show that this shows that the derivative doesn't exist. All right? Now, I'm going to argue the second part first. How is this exercise on top related to the fact that g prime of 0 doesn't exist? So let's go to the page and write the definition of g prime of 0 in general. So here's, for any function, right? Here's how we do the derivative, right? G prime of x is of c. In general, is the limit when x approaches c of g of x minus g of c over x minus c. That's the general definition of the derivative, right? So in this particular case, we want g prime of 0. And g prime of 0 would be the limit when x approaches 0 of g of x minus g of 0 over x minus 0. And remember that if this limit exists, then this limit will be the same regardless of the way you approach 0. So you can pick any sequence that approaches 0, right? So we can pick, so if g prime of 0 exists, then for any sequence xn such that xn approaches 0, we have that this would happen. If we put over here xn, we should get the derivative. We should get g prime of 0, right? So that's the idea. The idea is we're gonna pick a sequence that approaches 0. And instead of picking an arbitrary one, we're gonna pick a very specific one. So the idea here is pick the sequence xn equals 1 over 2 to the n. That one clearly goes to 0, right? Let me put it here. Clearly, xn goes to 0. Of course, right? It becomes actually very fast, exponentially fast. So if we put it in here, we should get g prime of 0. But now let's go back to the exercise. What is the exercise telling us that the answer is going to be? And this exercise is showing to us that the answer is going to be m plus 1, right? So when we put 1 over 2 to the m minus g of 0, 1 over 2 to the m minus 0, we're going to get m plus 1. And what is the limit of m plus 1 when m goes to infinity? Yeah, thank you, Andranik. That's right. It goes to infinity, right? And if it goes to infinity, that means the limit doesn't exist. And if the limit doesn't exist, then that means the derivative g prime of 0 doesn't exist. So that's what we want to do, right? So we want to show that the derivative at 0 doesn't exist because this limit with xn equals 2 to the n, let me change it to m as it was in the book. So I'll change the variable to m, and then we put m over here. That way it matches what I had read, right? So we're going to show that this limit doesn't exist. Okay, and how are we going to do it? Well, let's go back. Let's evaluate the limit, right? That's all we need to do. So let's do the exercise. So we need to see what is g of 1 over 2 to the m minus g of 0 over 1 over 2 to the m minus 0. That's what we need to do, right? Now, let's start with g of 0. What is g of 0 anyways? Well, in case you have forgotten, let's recall the definition of g, right? Our function, our very, very important function. What is the definition? I'll write it over here in this little corner. So we know that g of x is equal to the sum of h 2 to the n x over 2 to the n from 0 to infinity, right? And what happens when we plug 0? So if you plug 0, you get h of 0 over 2 to the n. What is h of 0? Remember, h is the function that gives you, you take the fractional part if the integer part is even, or 1 minus the fractional part if the integer part is odd. In this case, for every integer, as a matter of fact, right? If you go back to the h function, the h function goes up, down, up, down, up, down. And for every even integer, you get 0. For every odd integer, you get 1. So 0 is even, so this is 0, right? So g of 0 is 0. So that's the easiest thing of them all, right? So let's write then this expression. So 1 over 2 to the m in the bottom becomes 2 to the m on the top, right? And then we have g of 1 over 2 to the m minus g of 0, which I already convinced you that this guy over here is 0. Okay? You with me so far? Okay, next, we need to write down what g is. So that will be the sum from n equals 0 to infinity of h 2 to the n 2 to the n times x. What is the x? Is 1 over 2 to the m. Right? Divided by 2 to the n. Is that clear? Yes, I just plug it in. I haven't done anything. Now I'm going to simplify this a little bit. So continue over here. This will be 2 to the m. And then the series, the infinite series from 0 to infinity. Yeah, I'm going to write it like this. 1 over 2 to the n. H of, okay, so let's leave it actually. I'm going to write it like this. It seems like I didn't do anything. But I want to tell you a little bit about what we need to do here, all right? So let's think about, I want to break this sum in two parts. The first few terms and then the rest. And you may be wondering why. Well, here's the reason why. See, if your n is really big, right? For example, think about when n is already m. If they're equal, then this would be 1. And I know h of 1. H of 1 is 1. And then after that, if n is the next one, m plus 1, then if n is m plus 1, I'm going to have 2 to the power m plus 1 over 2 to the m. And that's going to be 2, h of 2. And that's an even number, so h of 2 is 0. I like that, right? I like it when I get zeros. If I plug the 1 after that, it will be a 4. And 4 is also 0, so I like it as well. So it seems like the important point where I should break this is when n is m. Okay, so we're going to break this into two parts. The part where we go from 0 to m. And then I'm going to write it like this, 1 over 2 to the m minus n, because m is bigger. And then I'm going to write the other part from m plus 1 to infinity. And for this one, I'm going to write it as h to the n minus m, because now this one is positive. Is that clear? Move it up a little bit. Okay, so close the bracket. So exactly what I was telling you, right? So remember that h of an even number, so little remark, let's put it here, remark, if h is even, if you plug an even number, if n is even, then h of n is 0, right? Our h function goes from all the even ones are in the bottom. That's where you get 0, and the odd ones are on the top, where you get 1. So all of these numbers are even, right? So all this big chunk is actually 0. And that makes me happy, right? I can then simplify it. All right, so that's awesome. Now, what about this part over here? Well, for this part over here, how about this number over here, 1 over 2 to the m minus n? Well, that's going to be when, for the last term is 1. And then before that is 1/2, and then 1/4, 1/8. So this number over here is actually always between 0 and 1. So note that 0 is bigger than 1 over 2 to the m minus n, which is less than or equal to 1, or n between 0 and m, right? So this number is, the highest is 1, and then it goes 1/2, 1/4, 1/8, right? Okay, so this number is between 0 and 1. And what is h of a number between 0 and 1? It's the beginning of the graph, right? So h of that number is the number itself. That's just the identity line right there, correct? Let me take you back to what I'm telling you here. So if we go back to our PowerPoint, to the graph of h, right here, if I have a number between 0 and 1, right here between 0 and 1, mark it with red, between 0 and 1, is just the identity line, right? Is y equals x. So that makes it super, super nice. So we can go back to what we were doing, and between 0 and 1, all of these numbers are between 0 and 1, so h of that is the same answer. All right? So let's continue. Continue over here. And so we'll have that 2 to the m that we have over here. The sum from 0 to m of 1 over 2 to the n. And we said this is the identity, so that's only 1 over 2 to the m minus n. And look at the beauty. Everything is going to simplify, right? Rules of the exponents. This becomes 2 to the m. And there's no n here anymore, so I'm adding the same number m plus 1 times, right? I'm adding 1 over 2 to the m plus 1 over 2 to the m plus 1 over 2 to the m, da, 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 between 0 and m. So that's going to be m plus 1 times 1 over 2 to the m. Of course, these guys cancel, and so we just solve the exercise, right? So this number over here is indeed m plus 1. Okay, so that's the end. And then, like we were saying, so thus, let's just finish it up here, thus the limit of g of 1 over 2 to the m minus g of 0 over 1 over 2 to the m minus 0 is the same as the limit of m plus 1, and that's infinity, which means it doesn't exist, right? So g prime of 0 does not exist. It also tells you more, right? It tells you that near that point, you have slopes that are becoming bigger and bigger and bigger and bigger, right? So the derivative fails to exist because we have a point where the slopes are of the secant lines are becoming closer to infinity. So one of those points where you have a cusp, right? A cusp that is vertical like this, right? Like I'm gesturing with my hands. That's what's happening at 0. Which corresponds to the idea, right? When we see the graph of the function, that's exactly how it looks at 0, right? Like a sharp turn because of a reason of being, you know, a cusp, a vertical cusp. All right, questions so far? Good. So let's go back to our slides and continue on our quest, right? So 1 point done. And infinity of them left, right? So we have shown that the derivative at 0 doesn't exist. Okay, that's 1 point. Actually, we have done more than that because our function is periodic, right? Our function is defined, it has a period of 2. So we've already also proved that the derivative is by periodicity. The derivative doesn't exist at 2, at 4, at 6, at 8, or 10. So we did more. And that's good. So we already have a bunch of points, but obviously not all of them. So let's keep going. What's the next? All right, now it says, next exercise, it says modify the previous argument to show that g prime of 1 does not exist, and then show that g prime of 1/2 does not exist. So we're gonna skip that one actually, because we're gonna do part B. Part B is even more general. Part B says, show that g prime of x does not exist for any rational number of the form some integer p divided by 2 to the k, right? For those of you that took 360 with me a few semesters back, these are like the dyadic integers. Okay, if you don't know what I'm talking about, don't mind, it's just a name. So these are rational numbers that have some integer divided by a power of 2. Okay, those are the ones we want to show the derivative doesn't exist. And it's gonna be pretty much the same way we just did for 0. Okay, so we're gonna try out the same thing. So our strategy is going to be to calculate a slope when we add 1 over 2 to the m, just like we did for 0. Okay, so here we go. Let's go to the page. So we're going to try to do this. This is what we want to do. So first, p is an integer. And k greater than or equal to 0 is also an integer. And what we're going to be doing is looking at this g of p over 2 to the k minus the other way around, actually. Let's put the big one first. Doesn't matter, but just to be organized. Plus 1 over 2 to the m minus g of p over 2 to the k, all of that divided by this guy minus this other thing. So this quotient is the one we're going to try, right? We're going to check what that quotient is. And if the limit of this doesn't exist when m goes to infinity, we're done. That would show that the derivative doesn't exist for g of p over 2 to the k. All right? So here's the idea. idea. That's our plan. Show that this limit over here, when m goes to infinity, does not exist. Right? That's what we want to do. Show that this big limit. Now remember here, there's a lot of letters here, but there's only one variable. The variable is the m, right? So these p and 2 to the k are fixed. P and 2 to the k are fixed, okay? All right, so it's not going to be difficult. We just need to evaluate these numbers. That's the only difficulty, all right? Well, first, also notice this simplifies already, right? So what is this one over here? The denominator. The denominator is easier than it looks because you're taking this number and you're subtracting p over 2 to the k, so this cancels, right? That cancels, so this is just 1 over 2 to the m. So really what we want to evaluate is this. This number divided by 1 over 2 to the m. And dividing by 1 over 2 to the m is the same as multiplying by 2 to the m, right? So let's do that. Let's evaluate 2 to the m times g of p over 2 to the k plus 1 over 2 to the m minus g of p over 2 to the k. Right? That's what we want to do. Evaluate this and then do the limit. And then do the limit when m goes to infinity. That's our plan. Okay? So here we go. So we need to evaluate these two. So let me start with the easiest of them all, which is this one, g of p over 2 to the k. So let's go. Let's do it. What is g of p over 2 to the k? Well, we go to the definition. So by definition is the sum from 0 to infinity, 1 over 2 to the n, h of a function, this number times 2 to the n. So 2 to the n, p, 2 to the k. All right. Looks complicated, but again, it will simplify a lot. So the same trick as the previous one that we did applies. Think of big N. When N is big, when N is the same as K, when N is the same as K, this will cancel and you get H of P. Now H of P is an integer, so H of P could be 0 or could be 1. So, okay, but not great. What if we go K plus 1? If N is K plus 1, then the K exponent will cancel and you're gonna get 2 times P. And oh, I like that. 2 times p, that's an even integer. So that's 0. And I like zeros, right? And if for even bigger numbers, even better, because for the next one, it will be for k plus 2, when you cancel, it will be 2 to the second power. So it will be 4. And 4p, that's also an even integer, 0. The one after that will be 8p, 0 again. 16p, 0. Beautiful. I love zeros because it simplifies things a lot. So the idea is the same. Let's break this into 2 pieces, from 0 to k, and from k plus 1 to infinity. And I'll write it like this, 2 to the n minus k times p. And then I will make precise what we just said, right? Because n is k plus 1 or bigger, this number is 2 to the first or bigger. So this is an even integer. Even integer. And because it's an even integer, this is 0, right? So this part over here is 0. All right, so we simplified it a little bit. So let's see what we have. It's from 0 to k, 1 over 2 to the n, h, and I'm gonna write it now like this, p over 2 to the k minus n, and I'm writing it like this because this is positive, okay? Now, the problem now is that we cannot proceed as in the previous case. See, I don't know what it is, because before we knew that this number was between 0 and 1, so we could do it. But right now, this number may not be between 0 and 1, right? I don't know. It depends on how big P is. If P is gigantic, then I don't exactly know where this is. So we're not going to worry about that. We're going to leave it there for a moment. And then let's try to do the other one. Let's try to do this. G of P over 2 to the K plus 1 over 2 to the N. Right? And let's think that the M is bigger than K. So let's leave for now. And let's work on the next one. So the next one is, and so let's assume M is big. So M is bigger than K plus 1. And then we want now to do G of P over 2 to the K plus 1 over 2 to the M. Right? So same thing. 0 to infinity, 1 over 2 to the N, H of this number times 2 to the N. That's a K. This number times 2 to the K. So let me write it as, how do I run it? Right. Well, I'll just do it like this. 2 to the N times this number. All right. So that's just the definition. Now, we can simplify it a little bit. And this time, so same as the previous one, think when N is bigger than M. When N is bigger than M, then this exponent will cancel this one because M is even bigger than K. So we'll cancel this one and it will cancel that one. And if we still have another 2 left, it will be an even integer. So that's awesome, right? We're gonna get 0 like over here again. So this time we should divide into three parts, from 0 to K. So let's remember that our numbers are like this. We have K, then we have M because so K is smaller like this, and then so we want to do between. Okay, maybe I should do a picture over here. Let me write down the integer line. So there's 0, and somewhere over there is K, and somewhere over there is M. So we want to do from 0 to K, from K plus 1 to M, and from M plus 1 to infinity. We're going to divide it that way, okay? So let's write it here. So from 0 to K, okay, so that's going to be 2 to the N times P over 2 to the K plus 1 over 2 to the M, plus from K plus 1 to M, and last from M plus 1 to infinity. Okay. Now, same as before, see, this one over here, the 2 to the N will cancel the 2 to the K and the 2 to the M and still have at least 1 extra. So this will be even. So this will be even integer. So this infinite sum, which is the problematic one, is 0. All right? So we're done with that part. Now, this first one, it's difficult, and we're going to leave it for later. But this one, we can figure it out. So let's figure out this one over here. All right? So what's going to happen here? So the N is bigger than, so let's simplify this. Let's multiply the 2 to the N by. So let's work on this one. All right, so it's the sum from K plus 1 to M. And I'm going to write it like this. H of, what is this? Well, the N is bigger than the K. So this is going to be 2 to the N minus KP. And then after that, what I have is, now the M is bigger than the N, right? Because N goes from K plus 1 to M. So for the other one, I'm going to write 1 over 2 to the M minus N. All right? Is that clear how I simplified it? Okay. Now notice, this is important. See, this guy is an even integer, right? even integer, because it's at least k plus 1. N is at least k plus 1. So this is k plus 1 minus k, it would be 2 or bigger, and then times an integer. So this is an even integer. So you have an even integer and you're adding a little tiny number, right? So what is h of that? Well, you need to remember that our function is periodic. The h function is periodic, right? So if you go to an even integer, it's the same as if you started at 0, right? It's the same as if you started at 0 because it's periodic. So this part over here is exactly the same. So the h is exactly the same as if you simply do h of 1 over 2, 1 over 2 to the power m minus n. Because this is like, it's the same as if you were at 0. Being at 0 or being at an even integer is the same for the h function because it's periodic. And this is a tiny number. It's a number between 0 and 1. So this is just 1 over 2 to the m minus n. All right? So this part we can simplify, which makes this part simply simplifiable as well. All right, so let's do it. Let's go back to the main one. So what is it that we have? We're going to write it over here. We're doing this one. We have the first sum that we haven't touched. I'm going to write it here. I'll actually multiply it by, so it's 2 to the n p over 2 to the k plus 2 to the n over 2 to the m. That's the first one. And then the second one, this one over here, we just made it better. So that's the sum from k plus 1 to m, 1 over 2 to the n, times, and we know now what the h is. The h is 1 over 2 to the power m minus n. And then plus 0. All right? Okay. Now, this obviously simplifies. It becomes 2 to the m, right? It becomes 1 over 2 to the m. Let's write it actually with the higher powers, positive powers in the bottom. So it's p over 2 to the k minus n plus, and then the m is even bigger, so that's 1 over 2 to the m minus n as well. And then this one we said is 2 to the m, so it's 1 over 2 to the m. And how many terms do we have? From k plus 1 to m. So that's exactly m minus k terms, right? Okay, great. So it seems difficult, but it's not. It's just, you know, detailed bookkeeping. So we're evaluating the sums, and we're careful to see which ones we can evaluate and which ones we can't. And this part we can't really simplify just yet. In fact, we won't be able to. But what we can do is we're going to be able to simplify it once we collect the two of them together, right? Remember, we did this one right now, and before we did this one. Yes, I said leave for now. So now it's the time to combine them. So now let's put together the two that we did. So what are the two together? So combine the two together and multiply by 2 to the m, right? Remember, let me remind if, in case you didn't know what the plan is, here is the plan, right? Our plan was to take the difference of these two and multiply by 2 to the m. So let's do it. So it's 2 to the m, the one we just did right now, minus, this is k, minus g of p over 2 to the k. And what is it? Well, this is the one we just did. So let's write it here. It will be this sum plus 1 over 2 to the m minus k. And then minus the one we said leave for now. And it's right here. Leave for now. It was this one, how it's simplified. So I'm just going to write it where we need it, okay? So it's the sum from n equals 0 2k, 1 over 2 to the n, h of p over 2 to the k minus n. All right. Perfect. So this is where we are. We're almost done with this part. And like I said, it's a lot of little calculations, but okay. So now the middle one, we simplifies, right? This 2 to the m cancels this 1 over 2 to the m. So it will be m minus k. And these two we can combine because both of them are from 0 to k. So let's combine them. So it's 2 to the m, the sum from 0 to k of 1 over 2 to the n times h of p over 2 to the k minus n plus 1 over 2 to the m minus n minus h of p over 2 to the k minus n. Okay, beautiful. Now it's our time to use the lemma, right? Look at these two numbers. Are they close? Are these two numbers close? This guy over here and that guy over here. Specifically, if I know what is the integer part of this number, do I know the integer part when I add a little power like this, 1 over 2 to the m minus n, you know, a little tiny part? And the answer is yes, right? So these two numbers have the same integer part. So note that if we have the integer part of this number, I don't know what it is, could be anything depending on p. If I add a little power, if I add 1 over 2 to the m minus n, well, the largest power I could be adding is when n is 0, right? So the largest this could be is when n is 0. And that would be 1 over 2 to the m, and m is even bigger than k plus 1. So this is certainly smaller than this one. So this is smaller than a plus 1. Okay, so these two numbers have the same integer part, which means I can apply the lemma. So what is the difference of these two numbers? Well, I don't exactly know. It's either one, it's either this minus that. Remember the lemma? So by the lemma, h of x minus h of y is either x minus y or y minus x, right? It's one of the two. So it's the difference times 1 or times -1, okay? So that's what I'm going to write. So it's one of those numbers, either times 1 or times -1. So here is what we have. So this is, continue over here, this equal sign that I put an asterisk is m minus k plus 2 to the m, sum from 0 to k, 1 over 2 to the n, and then either plus 1 is either the difference or minus the difference. So that's going to be plus or minus, right? And the way I'm going to write that plus or minus is I'm going to write an epsilon n, and then it's going to be this minus that, where epsilon n is either 1 or -1, right? So sometimes it stays the same, sometimes it flips, like we did over here. So it's either +1 or -1. So that's why I put this epsilon. And the important thing here is that this will cancel, right? Now this number goes away. This number 2 to the n cancels this 2 to the n. And this 2 to the m cancels with this 2 to the m. So look at all the simplification we achieved, man. We're so good. This 2 to the m cancels that 2 to the m. Well, let me leave that last step. So we have the epsilon n and the 2 to the m, which cancels. So finally, we get m minus k plus the sum of the epsilon n's. That's it. right? We finally simplified it as much as we could. Okay, now don't be concerned about this. I mean, it looks difficult, but it's just a constant, right? Remember, what we want to do is take the limit when m goes to infinity. We want to see what happens when m goes to infinity. And in that sense, we're golden because there's no m in here. These are ones and negative ones, so it really doesn't matter. And what happens when m goes to infinity? When m goes to infinity, this will go to infinity, right? So thus, the limit when m goes to infinity of 2 to the m times g of p over 2 to the k plus 1 over 2 to the m minus g of p over 2 to the k is this constant that we don't care and this number that goes to infinity. So it's infinity. So g prime of p over 2 to the k does not exist. Woo! Sweet, right? Okay, that's awesome. So now we have a lot of numbers for which the derivative doesn't exist. These numbers actually are dense in the real numbers. So if you pick an integer and you divide it by 2 to the k, you can, fill up a lot, but there are rational numbers, right? These are some of the rational numbers and they are dense, but it's not enough. We want to show it for every real number, right? So this is great, but we're not done. So let's go back to our presentation and see what follows. So we did this part, and then what follows is the last one, the last part. And this last part is, first we need to show this little lemma. And this is a general lemma. It's a general way of different way of defining the derivative. This general lemma says the following. It says, imagine that you have a function which is differentiable at some point a. At some point a. And then you have two sequences. You have the an sequence and the bn sequence. And those sequences are of numbers that are less than a or numbers that are bigger than b. And both of them go to a. Then you can do the derivative of a this way. You can do the derivative of a as the limit of f of bn minus f of an over bn minus an. And that's part A of this exercise. And part B is to use that lemma to show that g prime of x does not exist for any x, for all the other ones that are missing. Okay? So that's what we're going to be doing. Okay, let's do it. So first, we're going to do that lemma. So want to show. So let me write down my assumptions here. All right. So how do we do this? Well, it's actually not, this is not, I mean, there's a trick involved here to show this, and it's a nice general lemma in general, I mean, a useful lemma. And here's the thing. So what we do know is that because f is differentiable at a, we can do f prime of a by doing the limit using the an sequence. So we can do the limit when n goes to infinity of f of a minus f of an over a minus an. So we know this is true because an approaches a. And we also know it with the b sequence. So we can also do f of bn minus f of a over bn minus a. So we know this is true because both an and bn approach a and b.
Quick question, Professor?
Yes.
Are we sure bn goes to b? Because I thought it said limit of an and limit of bn both go to a in the book, or in the slide you showed us too.
Say that again. I didn't get it.
So I was saying, are we sure that bn goes to b? Because it showed that limit of an and limit of bn go
No,
both.
bn goes to a. My bad.
Oh, okay.
That's what it's called a. It should be called something different because it's unrelated to. Yeah, this is the way it's written in the book. I would have chosen a different letter. Yeah, both of them approach a. My bad. Yes.
Why choose a different letter if they both approach a?
No, because no real reason, but AN approaches A, and then you see how I made the mistake of BN approaches B, because I think A, N, and A are related in some way, right? So
Oh,
you see what I mean? So maybe we should change this to some letter that doesn't have anything to do with A, N, or B, N. How about U? Something
okay.
like that. You see? Because
Yeah.
it's A, the ANs and the A don't have any relation.
Right, right. That makes sense.
Yes. That's why I made a little mistake here, right? Yes. Thank you. Thanks for the correction.
Of course. Thank you.
So these two are like this. And here's the idea. I'm gonna show you something that I think we covered it way like almost day number 1 when we were talking about rational numbers and how they were dense. You may remember that if you take two rational numbers, like you know, which letters do I want to use? Let's use N1 and M1. Okay, so if you have two rational numbers like this, where one is bigger than the other, if you want to find one in between, you can do this. You can add up the numerators and you can add up the denominators. And that one is always in between. So for example, let's think of, 1/3 is less than 2/5, right? This is like 0.3 and this is 0.4. So this means that if you do 3/8, that's right in between. If you don't know why this is true, it's super easy. Just cross multiply and you realize that it's the same thing as the original inequality. If you cross multiply, so it's super easy to prove. This is true in general. And the beauty of this is, what would happen if you do it with these two? Right? What happens when I add up the numerators and then add up the denominators? So if I apply it to these two, the one in the middle would be f of bn minus f of u plus f of u. The f of u cancels. And then in the bottom, u minus an plus bn minus u. Again, the u cancels. Isn't that beautiful? That's exactly the one we wanted, right? Look over here. The one we want is precisely this. So here's the thing. This guy is always in between these two, right? It's always in between those two. So it seems like then we can now use the squeeze theorem, right? If you have a limit and the other guy is always sandwiched in between the two of them, and the two of them go to the same thing, then we're done. And that's the proof. There's only one little technical thing we need to take care, because maybe even though this guy is in between these two, it's not true that this is always smaller than that one, right? Maybe they flip at some point. Maybe right now they're like this, and then later for some n they flip, and then maybe they flip again, and maybe they flip again. See, it really doesn't matter, because this guy is always in between. But to use the squeeze theorem, in the squeeze theorem we had the hypothesis that it's always the first one is smaller than the one you want to squeeze, which is smaller than the bigger one, right? We need to have that inequality to apply the squeeze theorem. So we need to fix it, and it's an easy fix. So here's the fix. The fix is the following. So we're gonna think of this alpha. I'm gonna rename my sequence, and I'm gonna call it alpha n and beta n. And I'm gonna leave it the same as an and bn if this quotient is bigger than that one. So if they are ordered in the way that we have it written right now, I'm gonna leave them the same. And if they are the other way around, then I'm gonna change them. I'm gonna make the alpha n the bn and the beta n the alpha n, if the order flips. All right. Now, if we do this, The alpha sequence is either an A or a B, and the beta sequence is either a B or an A, right? We're only, you know, switching the sequences. So sometimes they're A's and sometimes they're B's. But both the A and the B go to U. So we still have the same for alpha and beta. So note that alpha n approaches U and beta n approaches U when n goes to infinity. So the sequences are still going to U. But now I always have the inequality that I want. But now f of beta n minus f of u over beta n minus u is always greater than or equal f of u minus f of alpha n over u minus alpha n. Now this one always beats that one. Why? Well, because if I didn't change them, it was happening already. Perfect, that's what I wanted. And if it was the other way around, I changed the names. So now, even though it says alpha over here, now this is called, the beta. So the beta is now the bigger one than the other one, right? So now this happens for every n. So now I can figure out the one in between. So use the little lemma for rational numbers that I was telling you, so that this little rational number is always between these two. So then by the squeeze theorem, the limit of f of beta n minus f of u over beta n minus u is bigger than or equal the limit. So what's the guy in between these two? When I add the numerators, the f of u cancels, and I get f of beta n minus f of alpha n divided by beta n minus alpha n. And this is in turn greater than or equal f of u minus f of alpha n over u minus alpha n. Now, I told you that these sequences both go to u, so this is f prime of u. And this is also f prime of u, which means the middle one is f prime of u, just as we wanted, right? So it means by the squeeze theorem, f prime of u is this. Now you may be wondering, but hold on, professor, we didn't want this with betas and alphas. We wanted it with alpha and with A and B. Well, yes, but what is this quotient over here, right? What is this quotient over here? So let me write it. What could have been the case? Either they stay the same. This could happen, two things could happen. Either they stay the same, in which case that's exactly what I want, right? Or they didn't stay the same, in which case I flip them. So this is really f of an minus f of bn over an minus bn. But look what I have. I mean, it's like multiplying by -1 top and bottom, right? If you multiply by -1 top and bottom, you realize that these are the same. So it's really the same. So we put that in here, and this is the limit when n goes to infinity of f of bn minus f of an over bn minus an, and that's the end of my little proof here. Okay? All right. Awesome. So that's this little lemma. By the way, this lemma is in general. It has nothing to do with our function that we were working with, right? So now we're going to use it. And so last little push. So we want to now show that the derivative doesn't exist at all the other points that are not p over 2 to the k. Okay, so here we go. Last push. So for every x such that x is not equal to p over 2 to the k. So those are the ones that are missing. with p integer and k greater than or equal to 0. For every one of these, you can do the following, right? Because it's not one of these guys, you can find for every k, right, for every m, so let me write it here, for every integer m, there is a unique pm, such that this happens. You have your x, and x is bigger than p over 2 to the m, but smaller than p plus 1 over 2 to the m. Correct? Yeah, if the x is not one of these numbers, you must be able to capture it between two of them, right? Doesn't matter what your x is. You should be able to you know, pinpoint it between two of these. Yes, let me give you a little example. So imagine that x is pi, right? And let's start with m equals 0. So I want to pinpoint pi between an integer over 2 to the 0 and the next integer times 2 to the divided by 2 to the 0. That's easy, right? That's the number 3. So we know that 3 is less than x is less than 4, because pi is between 3 and 4, correct? So it works. This p is the same as 3 over 2 to the 0, and this 4 is the same as 4 over 2 to the 0. Now, if you go m equals 1, now I'm using halves, right? So for halves, now I have that pi is less than 6 halves and 7 halves, right? Because 6 halves is 3 and 7 halves is 3.5, correct? If I go m equals 2, then I still have, now I have 12 fourths and 13 fourths. 13 fourths is, by the way, 3.25. And so on. Is that clear? So every number that is not one of these that we already did, we can pinpoint it exactly between two of these. And that's going to be important. So this is going to be our sequence AM, and this is going to be our sequence BM, right? And so it satisfies the hypothesis of the lemma we just said, right? The AM is less than X, and the X is less than BM. Both AM and BM approach X. So if you take the M bigger and bigger and bigger, then the difference between these two numbers becomes less than 1 over 2 to the M. So they're both getting closer and closer to X. So note that AM approaches X and BM approaches X. Moreover, so then if the derivative at X existed, so if G prime of X exists, then we must have that the limit when m goes to infinity of G of Bm minus G of Am over Bm minus Am should be G prime of X, right? That's the lemma we just proved. If this derivative exists, then this should be true. So to finish up, to show that the derivative doesn't exist, we're going to show this limit does not exist. That's the last thing we need to do, and it's going to be the last thing for today. So last thing we need to do is, so we need to show the limit of G of Bm minus G of Am over Bm minus Am, and m goes to infinity, does not exist. If we do that, we're going to be done, right? Because then the derivative G prime of X doesn't exist. So that's all we need to do, and let's do it. It's not going to be that difficult. So we just need to evaluate all of those numbers. And here's how we do it. So let's write what is g of bm minus g of am over bm minus a. All right. So first the denominator, bm minus am. So let me remind you, let's bring it over here, right there. So here's the definition. Am is some integer over 2 to the m, and bm is the next one. So the difference, this minus that, this number minus that one, is just 1 over 2 to the m. Okay? So this is going to be, in the bottom, is going to be 1 over 2 to the m. And in the top, we have the g function. So the g function is the sum from 0 to infinity of, so I'm going to combine them, both of them together. So this will be h of 2 to the n times p plus 1 divided by 2 to the m minus h 2 to the n times p divided by 2 to the m. All right? Just plug the definition of what bm is and what am is. Nothing more. Okay, now I don't need the definitions anymore. I can proceed from here. So this will be 2 to the m multiplying 1 over 2 to the n. And I'm going to write it like this, as h of p plus 1 over 2 to the m minus n, when the n is small. So this is only between 0 and m. And then when it is bigger, I should write it the other way around. So this should be h of p plus 1 times 2 to the n minus m minus h of p times 2 to the n minus m. And just as we were doing for the other problems, these are now even integers. And because they are even integers, h of them is 0. So all of these thing cancels. So this is 0. Okay, so all that we really have is this number. And well, we're going to use our lemma. Very useful lemma, right? We already used it many times. These two numbers are really close to each other. So they have the same integer part. They have the same integer part. So if this number p over, this is the smaller one, p over 2 to the m minus n, is between a and a plus 1, then when you add 1 over 2 to the m minus n, you're still less than or equal a plus 1. So you don't go to the next integer, right? Like, for example, if you have something like 7/8, 7/8 is between 0 and 1. If you add 1/8, you're still less than or equal 1, right? And I can change it to other numbers. So, for example, 22/8. 22/8 is between 2 and 3. If you add another 8, you're still less than 3, less than or equal, right? So that's exactly what we're saying here. So these two numbers have the same integer part. So when we do one minus the other, is either the same or minus the same, right? So h of x minus h of y is either x minus y or y minus x. So this sum simplifies as, it's either some epsilon n, which is 1 or -1, and then their difference. So it's p plus 1 over 2 to the m minus n minus p over 2 to the m minus n. This cancels the p with the p. So this is 2 to the m minus n. With this n becomes 2 to the m. 2 to the n times 2 to the m minus n. So the n's go away. So it's 2 to the m, and with that 2 to the m goes away. So all that remains is epsilon n from 0 to n. So it's 1, negative 1, and you don't know. It may be 1, 1, 1, negative 1, 1, negative 1, 1, 1, 1, negative 1, negative 1, negative 1, negative 1. I don't know, right? It's some sequences of ones and negative ones. But here's the thing. If you have some sequences of ones or negative ones, could that be convergent, right? Because what we really care is what is the limit. What is the limit of these when m goes to infinity? That's what we wanted to show, right? That it doesn't exist. So lastly, the limit of these, the limit when m goes to infinity of these sum of epsilons. So it's the same as writing it this way, right? By definition, right? It's like a series of ones and negative ones. Thus is not convergent. Is not convergent. Why is it not convergent? Well, by the divergence test. By the divergence test, because if you have a series that is convergent, the limit of the term should go to 0. Because the limit of epsilon n when n goes to infinity is not equal to 0. It cannot be 0 because it's either 1 or negative 1. This is the divergence test. So this shows that g prime of x does not exist. And that's it, right? We did it for all the numbers that were of the form p over 2 to the k, and now we did it for all the others, all of the numbers x's that were not p over 2 to the k. All right, that is it. That shows to you that this function is actually continuous, but not differentiable. All right, and I know I already am a couple minutes over the time. So I just wanted to show you another thing. So the original version of this was done not with this zigzag function. So if you're wondering, the first time that somebody showed such a function existed was Weierstrass, and he did it using not this type of function, but rather the sine and the cosine function. I just wanted to show you that little animation of what happens when you use the sine or the cosine. And so it's the function that he used was to add up cosine. So instead of using the h function, he used the cosine function. Think of it that way. So he did cosine of 2 to the k times x divided by 2 to the k. And I'll show you the graph over here. So the graph, here's the graph of cosine. Now I need to see the negative. Okay, so the blue one is cosine, and the orange one is 1/2 cosine of 2x. So it's the one that is half as big but oscillates twice as fast. And when you add the blue and the orange, you get the green. And that's the first step. And then for the next step, you take the blue one, and now you add this 1/4 cosine of 4x, the one that oscillates 4 times as fast, but only 1/4 the height. And then you get the green one, and so on. So it's gonna look like this. So this is the picture of the one that Weierstrass came up with in the first place, which is even more surprising because now each one of the stages is actually smooth, right? Cosine is smooth. It goes smoothly all over the way. Well, guess what? In the limit, you lose all the smoothness, right? Suddenly it's not smooth at all. Every point becomes a sharp turn, like you are seeing right here, right after several iterations. All right, so I just wanted to mention this to you, and I'm gonna stop soon. unless there are some questions. A question, Majid is asking if I'm gonna upload this lecture and the one before it. Yes, I have already uploaded the one before it. I guess I hadn't put the link on Canvas, but if you look it on YouTube, it's already uploaded. Or if you click on the one that has the entire playlist, you can find it. And as soon as I'm done with my next class, I'm gonna upload this one. Also, I will put the sample exam later today. All right, the sample exam number 2 will be posted later today, and the solutions to it next week. Okay. Any other questions? Great. Sorry for taking a bit more of your time. I'll see you guys next week. Stay safe.